so much, Miseo, for the nice introduction. And yeah, as he announced, today I'm going to talk about learning of quantum states prepared by Gaussian unitaries and a few magic gates that we will now introduce what this means. Like, I guess that yesterday or 2 days ago, you had the lecture by Francesco, my brother, where you already introduced the notion of learning, the complexity of learning general states. But yeah, today we will review just a few notions before going into the topic of today. So, like, um, second. So, like, learning. Oops. So, 1 second. I don't know why I cannot. Okay. Learning general states is hard. Like, and I guess that this, or you saw 2 days ago with my brother in the continuous variable setting, but it's also known in, I mean, in finite dimensional systems already that if you don't have any assumption on your states, rho, like if you have access to rho tensor n, like sorry, rho tensor n, and you want to run a quantum algorithm such that it output you a classical description of state rho up, such that in trace distance rho up minus rho is smaller than 10 to the minus 5, let's say. Then you need n that scales like omega. Like if you have n qubit system of n mode systems, like these scales like 2 to the omega n, or in general, like omega d square for a mixed state, or like omega d for pure states, if rho is promised to be pure. And these algorithms are known to be, I mean, these lower bound are known to be tight. I mean, there are quantum algorithms that achieve this. So this is bad because the sample complexity, the number of copies n of a general states to learn it scales exponentially. However, like we can expect that for restricted class of states, for physical constrained states, learning might be easy. Like and a few class of states that like people have considered in the literature have been like stabilizer states that I call just stub, that are states prepared by Clifford circuits. I mean, restricted class of states may be learnable, where for learnable, and now I'm going to make some example. Like learnable, I mean n that scales like poly n, where n is the number of qubits of your states, where d is 2 to the n in for n qubit systems, or n modes, or like it can be both bosonic and fermionic that I'm going to introduce soon. And also the time complexity of our algorithm. I mean, in this talk, I will always talk efficient, like when I talk about also computation efficient. And when I say learnable, I mean efficiently learnable. Okay. And examples of few class of states that people have considered in the context of learning to date are plenty. For example, stabilizer states, like also these what we will see again today that are Fermionic Gaussian states or are also called free fermions. And but also people have also considered like low entangled state, like MPS type states, states generated by shallow circuits, and so forth. Gibbs state, like so. I mean, people have shown that if you have some assumption on a state rho, then there exists a quantum algorithm that might use less copies of your state, like poly-n and t equal poly-n, to learn the state in trace distance, where trace distance, I recall, that is used for the tomography or learning estimation, state estimation tasks because of his operational meaning. And I mean, a way, for example, if we take stabilizer state, we know that stabilizer states are prepared by Clifford circuits that we know that Clifford are not universal for quantum computation. However, it's known in quantum computing that if we take like another class of states that has been shown to be learnable, is this, that is stub, the class of Clifford circuit that doped with a few non-Gaussian gate, Clifford gates that they call T-doped Clifford or stabilizer states, T-doped stubs, okay, with T equal log n. I will say more about this. And these are just states prepared, like we have a zero state, and we have planned a T gate, we apply another Clifford, then we have a T gate. Okay, and that this be shown that as also might be intuitive, that this class of states for all Clifford, I mean, possibly different, is admits an efficient quantum learning algorithm. And so it's natural also okay, these I mean, there were 3 papers that like you can find in the reference that Junseo shared, where I mean, all these reference or all these examples of states are referenced in the paper that Junseo shared on his homepage. And okay, so it's natural also to ask the same question for fermionic Gaussian states, where also in this case, or also bosonic. I mean, here I wanted to say the same for bosonic. Yeah, in this talk, we'll see that everything that holds for fermions and boson, I mean, is the same basically for this context. So it's natural to ask what if I have the analogous for, like if I have a Gaussian state, that this would be a Gaussian state, but if I start to add just a few like fermionic non-magic gates that are called non-Gaussian gate. I mean, is it basically the intuition that why, I mean, these states are not that complex. I mean, stabilizer states are efficiently classical simulable. while general states, no. General states might be efficiently reproducible with an exponential number of T gates. However, we know that if the number of T gates is low, the state is somehow not very complex. In fact, for example, admit also if the number of T gates is small, one can find an efficient classical simulation algorithm for these states under the reasonable notion of classical simulation. And the same holds true for few non-Gaussian gates. So far, I didn't define formally, but I will go later. I wanted just to give an introduction to this topic. And okay, so in this talk, we will quickly define better what Gaussian unitary Gaussian state is and T-dot Gaussian state is, and we will show how to learn them efficiently. And okay, so and we will review, of course, the basics of fermions and show the parallel with bosons. Is it all clear so far, or you have any question? Feel free to interrupt me at any point, of course.
Okay, so I have a quick question.
Mm-hmm.
So I believe all of those examples, like the stabilizer states or low entangled states or Gaussian states, T-dot states, I guess they're all also efficiently simulable. So is
Mm-hmm.
efficient simulability, like, is there any connection between efficient simulability and efficient learnability?
Okay. That is a very interesting question. However, there are examples of states that are efficiently learnable, but not classical simulable. I mentioned, but I didn't write, that are, for example, states prepared by, for example, 2D shallow circuit. It's not known if I mean if you can sample from 2D shallow circuit efficiently. However, there have been algorithms in the past few years that have shown how to learn both shallow circuits, unitaries, but also states prepared by this. So the connection that these are the states which are learnable, but yeah, it's not known to be classically simulable. So yeah, while it's intuitive, but I mean, it's there are different notion of complexity, but I would say that if a state is classically simulable, then might be also learnable, but I don't know any general theorem about that. I mean, it's basically, um, if one does not care about time complexity, then one can find the connection between how large is the class of states with the sample complexity. However, I'm not aware about time complexity guarantees. Like given that the class is sufficiently classical simulable, then it's sufficiently learnable. I mean, for the few example that I know, I think it works this implication, but the converse not. Clear so far? Okay. Then okay, I pass to to the topic of the talk that is adopt fermionic Gaussian learning, but also with the parallelism to bosons because it's more or less the same. But I will start with fermions. We'll have more emphasis since you have seen the basics already of bosons in the past few talks. So now I will talk about T-dot fermions. And let me start with a motivation. And let's start with the case at zero depth. I mean, t equals 0. Like we have basically what one would call free fermions or Gaussian state. And this state here are states that describe free fermionic particles like that do not interact with each other. I mean, and so they are particle non-interacting. For this reason, they are called also free fermions or also non-interacting fermions. However, if one wants to describe like some interaction between these particles, one needs to introduce some like so-called non-Gaussianity or some some sort of like magic in the system. In fact, fully interacting fermions systems are not known. I mean, one are basically general states, very complex states, and for this reason, we need. The notion of T-dot states makes sense because they describe interesting physics. Like already, free fermions can describe interesting physics, but I mean, to have more general physical phenomena, one it needs to introduce some interaction. It is captured by this non-Gaussianity. Okay, let me start with defining a few important notion. I guess that since this is a quantum computing course, you know, a lot. I mean, basically, like Pauli, if in quantum information based course, maybe you are familiar more with Pauli matrices. So, let's say that we have a system of n modes, or you can think also to n qubits, basically. I mean, a free fermionic state can also be taught as a qubit state via careful definition. And that's what I'm going to do in this talk. However, everything can be just taught in the fermionic language if one defines the fermionic Hilbert space with creation relation operator, as maybe some of you have seen in physics course. But here I'm going to just rely on the qubit picture. And it's important to define like Majorana operator that are the analogous of quadraturus operator that you might have seen in the previous lecture. And they are defined like in this way, like we have k minus 1 and we have a z string here, or this I might also write like a tensor product. And here we have xj, or we have the same zj and yj. Sorry, yk I wanted to write. And I mean, with this definition, one can see that Majorana operator, like gamma I, gamma j, anti-commute. I mean, if I is different from j, like to Majorana operator anti-commute. And this is actually the defining property of Majorana. They also square to the identity. And I mean, in particular, this definition satisfy, you can verify this property. Okay, now, like, let's define what is a Gaussian unitary. Like, G is Gaussian. G unitary. I mean, G, sorry, in U to the end is Gaussian if I leave G dagger gamma mu G is equal to nu 1 to the n o mu nu gamma nu with O in the orthogonal group to n for all u for all mu in 1 to n. Okay, let's start to this. I mean, this is a definition, if you want. There are equivalent definition. And here it means that if I Heisenberg evolve a Majorana operator with a Gaussian unitary, this is a linear combination of Majorana operator with coefficients that are given by an orthogonal matrix. Okay, so any Gaussian unitary, since Majorana operators I didn't tell, but from this definition one can also see that they form a basis of like Pauli, like product of Majorana operator. If I take products of Majorana operator, they form a basis of the operator space. And yeah, so from this fact, one can see that a Gaussian unitary is parametrized by an orthogonal matrix. I mean, any Gaussian unitary is completely specified up to global phases by an orthogonal matrix in 2n modes on 2n, 2n dimensional system. And that's also the reason why Gaussian unitary are classified similar. I mean, they are fully specified by this orthogonal matrix in a linear number, a dimension grown with linear in the system sides. So that's a fundamental fact from for their classical simulability. And okay, a Gaussian state for this talk that I will mostly talk about pure Gaussian state. It's simply so psi is Gaussian or free fermion if you leave psi exists G Gaussian such that psi equal G 0n. Okay, this definition that I'm using for this talk, one can use also more general definition for mixed state, like people find often say that free fermionic states, mixed state are Gibbs state of quadratic Majorana Hamiltonians. That means product of two of these of Majorana operators. Like people say H is equal H mu gamma nu is a free fermionic Hamiltonian, and if one consider Gibbs state of this, like exponential, like of beta H normalized, this is a free fermionic state or other equivalent definition. But yeah, for the purpose of this talk, I will not enter into this and stick with this definition. Okay, as I said before, this is also, I mean, these are a qubit state, a fermionic state we can interchange in this talk analogously. And so let me just do the parallel with bosonic. For bosons, we saw you saw quadrature operators. I mean, these are Majorana. But for bosons, you saw quadrature that are the R1, R2n that were X1, P1, Xn, Pn. And you also possibly saw the definition of Gaussian unitary similar to this. However, for bosons, we had at least with the zero first moment, you had a symplectic matrix here, like G S bosons. I can label bosons. Ri, R mu, GS. So with S symplectic. So it's basically really similar what the mathematics that we have here. So, oh, sorry. So okay, all this definition holds also for bosonic systems. Now, to introduce okay, let me say few useful stuff about fermions. Like so, it's we saw that if you have an orthogonal matrix, again, let me stress this in O to N, that means O transpose equal identity. These imply that I mean these up to phase identify a geo Gaussian unitary. Okay, and given O, I mean it's known if you have O, like you can go to this, you can compile. It's known how to compile a Gaussian unitary in terms of n square local qubit gates. I mean, Gaussian unitaries are efficiently preferable on a quantum computer, but also on a fermionic quantum computer, both both fermionic and qubits. Like you can decompose a Gaussian unitary like um, circuit complexity, let's say, is order n square local gates are sufficient to prepare to compile a Gaussian unitary given a general orthogonal matrix. And so yeah, you can if you have a Grassel description of this O, you can compile, you can efficiently on your device a Gaussian unitary O GO. And also, it's very important to mention something. I mean, given I mean, free fermionic states are very simple, and while okay, you can specify by O. However, to also connect to the mixed scenario that I didn't define, people when they talk about prefermionic state, they always talk about covariance matrix. This is also true for bosonic. We have seen in the previous lecture. I know that like the notion of covariance matrix or bosonic Gaussian state. You have seen that bosonic Gaussian states are fully described by their covariance matrix. Also here, it's the same. A I mean, as you can define for any state, not only fermions, any state, not only Gaussian, like any general state, the covariance matrix that here I'm using just this I convention, but it's just a convention with this minus sign. Okay. For you have seen yesterday the analogous definition with for bosonic Gaussian states, I guess, a few days ago. And okay, this covariance matrix, I mean, sorry, like I wanted to write with indices. Okay, this is like one can observe that by the anti-commutation property of Majorana operator, that this matrix is real antisymmetric. That means, okay, yeah, 0 transpose equal minus 0. Okay? And a general fact about linear algebra implies that uh, any matrix that is antisymmetric, if a real antisim, implies that A can be decomposed in this form, like O lambda, sorry, let me, with lambda that is equal to j equal 1 to n, minus lambda j. Okay? And one can also see that in our case, this matrix here, the eigenvalues of this matrix must be smaller or equal than 1. Like just because these are Pauli. And one can try to see that the operator norm of the covariance matrix is smaller than 1. And it's not difficult to prove from the definition. And one property that in our case we will use is also that this lambda j, for our case, in general, not for any antisymmetric matrix, but if I have the operator norm that is smaller than 1, these lambda j are between minus 1 and 1. Okay? And since I have a minus sign here, I can, without loss of generality, take them positive. But yeah, never mind. And if I have a covariance matrix, I can always write in this nice form. And that's nice. And an important thing is that free fermionic states are fully specified by C rho, okay, by the covariance matrix rho. And given the covariance matrix, you can do lots of stuff. Like you can compute basically every quantity of interest, many quantity of interest that you want, like Pauli expectation value, Majorana expectation value, overlap with computational basis states. People talk about when they want to compute Majorana, like product of Majorana or Pauli expectation value through the covariance matrix, they talk about Higgs theorem. Yeah, and it is basically efficiently why this kind of values are efficiently classifiable. Okay, so if you have the covariance matrix, that is again a matrix 2n times 2n antisymmetric, you have basically a fully nice description of your free fermionic state rho, possibly also mixed, but here we will focus about pure state, pure Gaussian state. And actually, for pure Gaussian state, one can see that if I have C psi, actually this lambda, if I put in this normal form, this lambda must be 1, okay? And for if psi is a pure state. And importantly, one a way also to see this, it's due to this property. One can check that if you have, let's say that we have 0, and we consider CGO dagger rho G, okay? Or sorry, GO rho G dagger O. Okay, and asks how the covariance matrix change. The covariance matrix change exactly with this orthogonal matrix. Okay, this is an evolution how the covariance matrix change if I evolve my state, and that's with a Gaussian unitary, and that's also the reason why free fermionic states are efficiently classically simulable. As a trial, one can try to compute the covariance matrix, the correlation matrix of this state here. And I mean, it's not difficult to see from the definition that the covariance matrix of this state here is just this -1, 1, 0, 0. Okay? So if I apply this property, if I apply Gaussian unitary on this, I mean, if I have a pre-fermionic state, I have G0n, 0n G dagger. And so applying this property, if the covariance matrix is just J equal 1 n 1 minus 1 0 0. Okay, so pure free fermionic state have normal eigenvalues that I call this lambda j normal eigenvalues 1. Okay. Pure Gaussian. And for the bosonic case, you have the same, but you have the symplectic matrix, and here you have a diagonal matrix here. Okay. So far you have any doubt? Okay. Do you have any doubt before I go into details of TDOPT? Okay, I guess I can proceed. Now, so that's also the reason why free fermionic states are efficiently classically simulable, because you can start from the zero state, apply orthogonal matrix, and these are all linear algebra operation. It takes polynomial time in the number of modes. If you can evolve, you can just track through this by matrix multiplication, which is totally efficient. That's basically you just are tracking out the covariance matrix, and then given the covariance matrix, you can compute many properties efficiently. There are known formula for many things. However, to start to put less triviality in these states, one can define magic gates or non-Gaussian gates. Okay, actually, before I said, okay, I gave you this definition of Gaussian unitary. However, one can also, it's also known that a Gaussian unitary is basically a time evolved, like you can write like quadratic Majorana like evolution, like properly, I mean, H3, where H3, I said before, I mean, it's a quadratic, it's quadratic in the Majorana operator. However, if one defines like, one can define like a magic gate, like that is, this is quadratic, sorry. Quadratic Majorana, that means something, the time evolved would be something like this, the Hamiltonian, properly such that is with I factors such that is Hermitian is this proper time evolution. However, so this is a Gaussian. However, when we don't have some sort of non-Gaussianity, we have to break this quadraticity, and an example of non-Gaussian gate, for example, is this. Or you can just have different indices like gamma mu, gamma mu2, gamma mu4 with these indices in mu j in 1 to n. This is an example of non-Gaussian gate, and like because it's has more the product of more than 2 Majorana. And but in general, one can have any local Hamiltonian that is not quadratic here. A local, I mean, that involves just few indices. Okay, I mean a constant number of modes, or of this index, constant in the number of n. And okay, so and let me just for completeness, I just say this is a k local non-Gaussian gate where these are possibly non-overlapping. And in general, I can also, I mean, with the I factor such that, this is like a proper Hamiltonian. And I mean, here means Loppi, since Majorana, I mean, this I factor, one needs to be careful in depending by the number of Majorana, in order this to be Hermitian, like one might or might not need this I factor. And like, for example, in 4 case, yes, one needs. And so I'd also say k local non-Gaussian gate if I put some coefficient here, like if I take a linear combination on these of the same modes. Okay, and the same for when one would say qubit local gate. And so now I will introduce the notion of T-dot state, T-dot Gaussian state. And at T-dot Gaussian state, we saw that basically this is a pre-Fermionic state. However, if I want some non-Gaussian, I just start to put GT plus 1, W, let me say, just to have the same convention of the paper that Junzio shared. WT, GT minus 1, W1, G0, 0n. And where these are Gaussian, and these are k local non-Gaussian. That for the purpose of this talk, if this computes, I mean, we can just take 4 local non-Gaussian, k equal 4. Like, for example, gamma mu1, gamma mu4. With this theta that is real. Okay, and these are the modes between 1 and 2 and so this is for me a T-dot Gaussian state. And so far, do you have any doubt? Now we'll show, given this definition, we'll show some property of this state, or at least we'll claim and give an intuition. Okay, so WT is, we can say it is in this class. And okay, so we will also adopt the like this is also I will denote like UT, and I will call like T-dot Gaussian unitary. Okay. So T-dot state are the states prepared by T-dot Gaussian unitaries. And like one important theorem that maybe my brother spoiled 2 days ago is what we call, T-dot magic compression theorem. That is what underlies the learning algorithm. Okay, this theorem says let's say that psi is a T-dot state. Okay, then there exists a G Gaussian such that G psi is equal to pi tensor 0 n minus t, where this is like basically or equivalently, psi is J dagger applied to phi t tensor 0 n minus t, where exists G Gaussian and phi in a state in the C 2 to T, T2 tensor T, the first T qubits or T nodes. And this, means basically that a T-dot state, let me just take the paper just to take the image. Like basically, a T-dot state we show that admits this form. It holds this theorem just says this. Any T-dot state can be rewritten in this form, where this is a general states on OT qubit that I called phi. In our notation, okay, let me change just notation here just to match the figure. Here I call the G dagger, exists G such that G dagger psi equal this, and then multiplied by G, we have this. So, this is what we show. And these are basically Gaussian unitaries, as I said. These are local non-Gaussian, and this is a unitary supported only in the first qubit or only in the first order T nodes, and this is a Gaussian unitary. And okay, and this rewriting is then the underlying reason why how our learning algorithm works and is efficient. And so, do you have a doubt about this rewriting theorem? Just says that if T is small to fit here to be is T small the number order number modes, then T-dot state can be rewritten in this form. And the proof of this, I didn't show, but maybe if I have time, I will hint some details about the proof. Okay. So far, it's clear the theorem statement. And the same, by the way, holds again for bosons. Here a bosonic non-Gaussian unitary is just the analogous of Majorana operator that are just quadrature operator. Okay, so this compression theorem we show for fermions, for bosons analogously. Here I'm not saying fermions, and yeah, I mean match gates. By the way, like this figure is taken by the Fermionic paper, and like basically match gate is the way that people also call Gaussian unitary when they are talking in the qubit language. I mean, a match gate circuit is basically a Gaussian unitary. Okay, so I can continue. I will not prove this theorem now. Maybe at the end I will give some sketch if there is time. But this is a structural theorem of these magic states, magic fermionic and bosonic states, such that allow us to efficiently learn them. And actually, we define these states here, the states that are of this form, that up to a Gaussian unitary are a general state only on T qubits. We call them T compressible. Okay, so psi is T compressible if your leaf exists G Gaussian such that psi equal G phi tensor 0. Okay, n minus t, where n minus t here just mean 0 tensor n minus t. And so we show that basically again psi is t dot if this implies that psi is order T compressible, where order T hides this kappa T constant, where kappa is the locality of this, like for K. And like so basically this without our own notation, this is kappa T, where kappa in our case was for quartic interaction. Okay, so assuming this theorem, like if we have that our fermionic state is sorry, our bosonic or fermionic state is T compressible, we have just this sorry. Never mind. Like so I mean, what if we can learn basically G? So the strategy is given access to, we have access to psi G pi tensor 0. If somehow like we can learn G somehow, then we can undo it. Like we can compute G dagger psi, and we will just have phi tensor 0 and minus t. So we would have just a state supported on T qubits. Learn G somehow. We'll say later how. But if we learn G given access to few copies of psi, then we can apply and do full. We know that the state that will be supported only on T qubits, so we can just do full state tomography here. On the first T qubits or T mods, like let's say mods. Okay, on the first, yeah, like here I'm show how. psi is T compressible. Okay, so the algorithm is very simple. If we have a state of this form, if there is a way to learn G, we can just undo it, and then the state will be approximately of this form. We can do full state homography here, and that would be basically finished if we can learn G efficiently, because basically what this would show is that the sample complexity is the sample complexity to learn G. N sample to learn G plus N sample to T modes tomography. I mean, first T modes tomography, where we learn phi. So the sample complexity will be this plus, the sample complexity of this, as I said before, is order 2 to the order T. I mean, at the beginning of the talk, I said that pure state tomography or takes, mixed state tomography takes 2 to the numbers, order number of qubits, so 2 to the T. And the task is just to learn this G. However, one way to learn this G, okay, now I assume that one can learn this G, and I gave an intuitive working procedure of the algorithm. But a way to understand what I've told you before, covariance matrix, correlation matrix is very important to describe fermionic systems, to Gaussian state. One might also think that that's also true if we have few non-Gaussian gates, if the correlation matrix description might have some usefulness. So if we have psi, given access to copy of psi, and we look at the covariance matrix, which structure has this covariance matrix? Okay, first of all, I can for sure apply this Gaussian unitary, so this holds C psi orthogonal pi tensor 0. Okay, orthogonal transpose. Okay, if I have a T-dop state, psi T, the covariance matrix has this form where I have the covariance matrix of this product state here. And I know that it's known that product states like this, have the covariance matrix is the direct sum of the two covariance matrix. So I have basically C phi T plus C 0 n minus T. But this we saw that is basically J equal 1 n minus 1, 1. Okay? And this I can also write like OT sum lambda j 0 0 OT transpose, or another label. And so I can englobe everything in this covariance matrix, and I have some O, another O that captures also this orthogonal here, plus j equal 1. Here I have from j equal 1 to t. Sorry, here I have j t plus 1 to n. I have j equal 1 to n with something like, okay, actually, let me write explicitly this. I will have the first coefficient that are, sorry, lambda 1, lambda 1, lambda 2, lambda 2, and lambda t, lambda t. And then I will have 1, minus 1, minus 1, 1, 1, 0 on the diagonal and 0 on the rest. Okay? So, t-dot state, where this O is an orthogonal matrix. Okay? So, t-dot state have basically like the last n minus t normal eigenvalue are all one, while the first can be, so if I have my normal eigenvalue that I defined before, that diagonalize the correlation matrix, like I wrote it here. Okay. So these for a free fermionic state are all one. However, if if I have a t-dot state, the last n minus t are equal to 1, while the first t are less strict, I mean, smaller equal than 1, but these are imposed to be 1. Okay? And so they became small if I add non-Gaussian gates, the symplectic eigenvalue. So these are also some sort of proxy for non-Gaussianity. If one can estimate the covariance matrix or compute the covariance matrix and looks at the normal eigenvalues, if they are all 1, it's Gaussian. If some of them starts to be less than 1, there is some degree of non-Gaussianity in your state. And so if I have C psi, like the algorithm is just estimate S psi. I mean, let's say that I have the full classical description as C psi, and I put, since it's t-dot, I can apply an orthogonal matrix such that as this description here, I can order the symplectic, the normal eigenvalue such that I have minus 1, minus 1. I mean, sorry, just to be less messy, let me. I have here j equal 1 to t, lambda j minus lambda j, 0, 0, and then I have plus minus 1, 1. And so a t-dot state has this form here, at this covariance matrix. So I know that, I mean, and if I take, if I diagonalize so like an algorithm to learn that G is just takes C psi, and roughly you can estimate, like, let me say again, how to learn G. That was this step here. Learn G somehow. Okay? Given access to psi. So we have psi, and with few copies, we estimate C psi. Okay? Like with a C at. In some precision, like one can say, for example, operator norm, but for the purpose of this talk, I will not enter into the accuracy details. And like, I mean, let's assume that we have a fully classical description of this S psi without error. Like then C psi can be written in this form as above. And the one like A lambda or transpose. And the ones that you run these subroutines on C lambda. I mean, you can like observe that like you can try to define this state here. G O transpose dagger psi, where psi and this G O dagger, okay? And look at the covariance matrix. I mean, you can define this state that hopefully is what like is our compressed state. But if we compute this covariance matrix, this would be just a dagger transpose because dagger, I mean, takes basically G O dagger, I didn't say before, is equal G O transpose. One can verify from definition. And or -1 to have the connection. Yeah, never mind. Like so this is equal to C psi psi or yep, like O. But however, C psi was O lambda O transpose. So one can expect that I mean, it's not that this is the proof, but I mean, like one can expect if ODAG, I mean, if this approximation is very precise, like then this in such a way, like would be roughly like the identity. If this would be really O, okay, an orthogonal matrix, and this lambda here is a covariant is a matrix such that okay, in this case I wrote like this, but one is fine also to have something like a covariance matrix. Like basically this can describe the covariance matrix of a state supported on the first qubit. Like I mean, as I wrote here, plus this, okay, plus -1 1 0 0. So basically, if you learn, if you estimate the covariance matrix and you put in this form and you define this state here, one can see that with high precision, like so the true statement is that with high precision, if you do this procedure, this state will have roughly this covariance matrix here. So basically, from these, since these are basically Majorana expectation value or basically Zn expectation value, like if one looks what are the off-diagonal terms that corresponds to this expectation value, one see that are just Z. So from this one can recover that here the state on these modes needs to be the zero state. I mean, like if you call this state rho, the fact that here you have like the trace rho zj is just up to would be exactly 0 to j minus 1 to j. So in the here we are observing that this is 1 for psi, if rho is equal to psi. For all these indices. But if this is 1, means that the state needs to be like of the form this state here. Okay, let me call psi tilde, sorry, because it's the bold one. Psi tilde, where psi tilde, I mean this. Psi tilde needs to be of the form tensor 0, because it's the state that maximizes the expectation value. 0, all these modes where this is 1. And here we have a generic state. Okay? But our phi tilde was g tilde g at, sorry, g at dagger psi. So, so we we know that now if we apply g o dagger psi, we have a state of this form, and we can do full state tomography here and have an approximation of p at t. So the procedure is just this, that is explained intuitively, not in full detail. I mean, if we have access to psi, we can just compute his covariance matrix. Through his covariance matrix and his block diagonalization, we can learn O. I mean, learn G somehow. Now I will expand here more via covariance matrix estimation. Then, given the covariance matrix, one can put in the normal form, and through this O, define, use this O here. I mean, say my G is the one that has this orthogonal matrix, and you have this form, and then you do full state tomography. So I mean, like the covariance matrix is a matrix 2n times 2n with Pauli expectation value as entries. So the estimation procedure takes poly n time and sample. Like a naive procedure is to estimate element by element the expectation values. Like again, the covariance matrix elements are just Pauli expectation value or Majorana expectation value, or in the Bosonic procedure are also expectation value written in terms of expectation value of quadrature operators. And one can estimate the covariance matrix precise enough such that procedure work. And so the time complexity, sample complexity, our algorithm, the sample complexity, let's say, is just poly n, that is the samples required to estimate the covariance matrix precisely, plus the complexity for full state tomography, that is 2 omega t. Okay, roughly. And sorry, 2 order t. So in order to learn a t-dop state, you have a sample complexity that is poly n and 2 to the t. And so if t is log n, this implies that n t-dop is poly n. Okay, because 2 to the log n is equal poly n. And also the time complexity is these all the operation that we used here are just like linear system of equations, and so I mean really takes a Boolean time. So until t, if t is smaller than log n, if t is order log n or smaller, the time complex is Boolean. However, if t is larger than log n, the time complexity becomes strictly larger. I mean, from this. And for like NT super poly, I mean, it's starts to become too omega log n dominated. And so basically, one can try to see if this is necessary. I mean, actually, for T compressible state, for state of this form, not T-dopt, general than T-dopt, where phi is an arbitrary states, this is necessary since this is I mean, basically this is a generic state on the phi qubit and requires for full state tomography 2 to a t for T compressible state. However, for T-dop state that are just a subclass of T compressible, this I mean this existence argument does not hold. However, we show in the paper that if one any time efficient, there exists no time efficient algorithm that if it is omega log n, if you up to standard, I mean up to standard cryptographic assumption that I will not enter in detail, like LWE style assumption. And yeah, we use theory of pseudo-random states. If anybody heard about, to show that if t equal omega log n, there exists no time efficient algorithm for T-dot states up to crypto assumption that we say in the paper. Okay, and this we showed for fermions this crypto assumption for bosons not. We had, but this argument of decompressibility hardness holds. And so again, we the recap, and I'm I will conclude soon because I think that there is not much time. But then I mean, if I will ask for question. So we saw that T-dot state, I mean, free fermionic state, free boson states are efficiently learnable. You can just learn the covariance matrix. I mean, so Gaussian are learnable, t equals 0. Unlike general states, like t infinity. I mean, just learn the covariance matrix. Just covariance estimation. And in this lecture, we also hinted, showed that if we have T-dot Gaussian, like a way to interpolate between non-Gaussian and fully geometric state. If T is order log n, then learnable. If T is larger, I can use this notation omega, small omega for larger, not learnable. And a reason for the learnability is our magic compression theorem that T-dot state psi t. I mean, exists a G such that G dagger psi t is equal to pi t tensor 0 tensor n minus t. So the strategy is just try to learn this compressing unitaries, and this is learn G via covariance estimation via C psi t estimation and block diagonalize it and the normal form that is that block diagonalization. Sorry. And diagonalization, such that you can write O lambda O transpose, and you can call these to GO and compile it. Okay, so this is like the overall idea of why T-dot Gaussian states are learnable if T is small, and also all of these both in the Fermionics and bosons. And I skipped proofs, and however, like okay, the proofs of this most I mean structural theorem of this lecture is just to I mean apply the Gaussian unitary definition that we had here, and try to manipulate this equation such that each non-Gaussian gate is Heisenberg evolved with a Gaussian unitary, and you try to put some other freedom to fix. I mean, you find some freedom to try to squeeze all the non-Gaussianity on the first modes, and all this turns out in a very nice linear algebra problem. I mean, it's okay. If you want, I can answer it in some detail, but you can find in the paper the proof, and it's and at the end, if you just try to a way to Heisenberg evolve this W1 and try to put a Gaussian unity that gives you some freedom to move the non-Gaussian everywhere, it's one finds easy the proof of this theorem. And then we sketch the algorithm, which is intuitively, but one needs to do the accuracy analysis well, like say with which precision we estimate the covariance matrix, we have here really zero or not. So I mean, it's but it's a bit subtle. I mean, it's not as easy as I said. One needs to be a bit careful on the error estimation of all these steps, but yeah, this is the overall idea. So okay, thank you so much for your attention, and please tell me if you have any doubt and questions.
Great. Thank you very much for that lecture today. And yeah, is there any questions from students here?
I have a question.
Mhm.
First of all, thank you for your very wonderful lecture. And you defined the Gaussian as the sum of orthogonal metrics and the gamma matrices. And can you explain more intrinsically why you define this kind of metrics as Gaussian metrics?
Okay. You want to know the reason why Gaussian unitary are called Gaussian?
Yes, yes. Oh, we can intrinsically think about the normal distribution if you call this state as Gaussian, but I cannot
Ah,
find a relation between this matrix and Gaussian.
okay, that's a wonderful question. I mean, so you are questioning why the name Gaussian if there is no really analogy with Gaussian distribution. Okay, I mean, I think yeah, the reason is for the bosonic case. In fact, if one looks at distributions over outcome measurements or like I mean, in the bosonic case, Gaussian states have some distribution which is a classical distribution that describes interesting property, which is Gaussian, and is described by the covariance matrix. I mean, this makes more sense. I mean, from the physics point of view, in the bosonic case, and in the fermionic case, I think Gaussian is just brought from analogy, and yeah, to the bosonic case. I mean, Gaussian states have so-called Wigner function or distribution of heterodyne, homodyne measurements, which is fully described by a classical Gaussian distribution with covariance matrix associated to the quantum covariance matrix. So that's the reason why the name Gaussian for the bosonic case. For the fermionic case, I guess it's just bringing the notation, the terminology from the bosonic one. Clear, more or less. But yeah, I mean, it's just a notation called Gaussian.
Thank you.
Yeah, and in bosonic case, Gaussian states are called Gaussian because I would say many things related to Gaussian states turns out to have underlying classical Gaussian probability distribution.
Great. So is there any other questions from students here? So maybe can you briefly touch some open questions in this field?
Okay, I mean, actually, I mean, for fermions, I mean, I guess for fermions and bosons, I guess many things that have been done for qubits are not really much explored. For example, I don't like all these Gibbs state learning different scenarios under this different assumption or are not that explored in the bosonic and fermionic case. I mean, there are works, but I don't think probably there is a strict for the same kind of generality that has been shown up to my knowledge in the qubit setting for learning Gibbs state of fermionic and k-local fermionic and bosonic Hamiltonians. And also an interesting open question that I think, I mean, basically optimal algorithm, efficient. Efficient, optimal, time efficient, optimal for learning Gaussian states is open. I mean, like it's known that sample-wise, it has been rigorously shown recently that n square over epsilon square is sufficient and necessary. However, the time complexity is unclear for that algorithm. And this was a recent paper by, in the Fermionic case, by Michael Walter and Frick, about Gaussian, group purification channel, where they show this as a corollary of their results. And however, there is no still time if one would like something like n sample and T complexity equal poly n, and possibly using single copy or few copies measurement, while these algorithms, it's not clear. The time efficient, if it may be time efficient or not. So basically, efficient time efficient algorithm that use, for example, a few copies measurement, few entanglement measurement for learning Gaussian states with optimal sample complexity and square is still open. And this is one question, but also, so one would like a matching upper lower bound, like possibly, for example, is it possible to show n square like epsilon square sample algorithm, sample complexity algo using T equal poly n as well? That's the question that is still open, that I think would fully match, complete the picture for learnability of Gaussian states. And also, the tight, here we showed that this scaling is roughly optimal, but having tight and really bound, is in n and in n is still open, like in the Fermionic case, time efficiently. But we showed polynomial time, but it's not clear if one can keep it experimentally feasible, like using single copy and be also information theoretically optimal. Another important point is testing, optimal testing. That is, if you have a state psi decide is Gaussian, okay, possibly, you will see tomorrow more about this, but it's still open up to my knowledge if it's a order one copies tester is can be found for fermions and bosons. The testing algorithm scales with system size still, and or with the energy in the bosonic case, I guess. But Filippo in the next lectures will say more about this. So yeah, for fermions, at least optimal testing algorithms are still open, and also optimal, let's say also in the Gaussian states case, a fully efficient optimal algorithm is still open, unlike the stabilizer case, for example. So these are two important, well-defined questions that I think are open still.
Great. Awesome. Is there any
Okay.
more questions from students? Okay, so.
And okay, let me say that I was not precise on the proofs and theorem statements. It was mostly intuitive explanation, but you can find everything in the paper that Junseo shared in his home page.
Great. So yeah, maybe we can finish our lecture today. And yeah, thank you again very much for Antonio.
Thank you so much.
Yeah.
And I really appreciated your invitation for giving this lecture. And yeah, okay, hope to see you at the QAP in a few
Yeah.
days.
See you in 3 days. Nice. Yep. And have a nice
Bye-bye.
day. Bye-bye.
Thank you.